All right, guys, we're going to look at some circle rules here. Okay, so we've got 3 circle rules I want to introduce. We'll kind of go through a quick proof of them, maybe do a few example problems, and then that'll be good to go. I'll try to keep it at 20 minutes or so. So let's jump in. And I'm actually going to get to the first rule real quickly. And if you notice what we have here, we have 2 chords intersecting inside a circle. And the other day we learned about the angles that they form. Today I want to talk about the lengths of the chords. So here's my first rule. It's going to be that CQ times QB. So notice, if I switch some colors, right, it's these 2 chords. So how chord CB was broken into 2 parts, CQ times QB is equal to, if you guess DQ times QE, you are right. It's equal to the product of these 2 other, we'll call it mini chords. They're not really mini chords, but you can kind of think of them that way, okay? So CQ times QB equals DQ times QE. Now, let's think about why is that true? I could be totally making this up. So, to get you started, okay, I'm going to encourage you to pause the video in a minute, maybe try to think through the proof. But to get you started, I'm going to draw in a line there and a line there, creating 2 triangles. So I'd encourage you to pause the video for a second and see if you can prove that CQ times QB equals DQ times QE. All right, so hopefully you gave it a shot. If you didn't, that's okay. But I would encourage you to try to do it. You'll learn more. You'll get a better sense for it. You'll learn it better if you try going through it. But let's talk through this proof here. So the first thing I might say is, what do you know about these 2 triangles? Well, I do know that because of vertical angles, these 2 angles have to be congruent. And so let me choose a different color. Arc DB here, notice it has 2 inscribed angles that intercept it. One being angle DEB, that intercepts arc DB, as does angle DCB. Now, if you notice, they both share the same arc. Those angles must be congruent. They must be congruent. So if that's true, if they both must be congruent, then that means those 2 triangles are similar. So the first thing I might say is that triangle DQC is similar to triangle EQB because of the AA theorem. Okay. All right, well, if that's true, if you remember your angle theorem or properties of similar triangles, we could then match up corresponding sides and say they're proportional. So I can match up DQ over QB. Let's take a look at what that is. DQ being opposite the 2 dash mark in the smaller triangle over QB being the side opposite the 2 dash mark in the larger triangle. That should be equal to CQ over QE. Let's take a look at those. CQ being the side in between the vertical and inscribed angle, in QE also being the same in that larger triangle. So what would my reasoning be? I might say that, similar triangles have proportional sides. And then given that, we could just quickly cross multiply and say that CQ times QB is equal to DQ times QE. And my reason just might be cross multiply, right? Properties of a proportion. And let's say we've proven it. If you go back to the top, we said CQ times QB would equal DQ times QE. And down here we just proved it. Okay, so just to quickly review, proof's good to know. But in reality, what are we really talking about? When we have two intersecting chords, the product, okay, of the two smaller, again, they're not chords, but we'll call them that for now. The product of the two parts that each chord is broken up into is equal to each other, right? So those two parts in red multiplied by each other are equal to the two parts in green multiplied by each other. All right, so let's go on to the next one. Now here I've got two secant lines intersecting, okay? And my proof, or not my proof, my rule here, I'll give you the rule right now, is that IG, so notice IG being the part outside the circle, times IH being, now pay careful attention, IH is that entire side outside, or excuse me, the entire length of the secant, is going to be equal to the same thing on the other secant. So IK times IJ. Okay, so if I want to highlight that, that would be IK, that's the portion outside, times the entire length of the secant. Okay? Now, just like we did before, I want to do a quick proof of this, and I'll get you started. I want you to draw in a line connecting GJ, and I want you to make a line connecting H. Okay. Give you a second to think about it. How could you prove these two triangles congruent? All right, so hopefully you paused it, gave it a second to think about it, and much like the last one, we're going to try to prove these two triangles similar. Okay, so notice the two triangles, and the two triangles, just to be clear, I'm really referring to is this triangle in blue, okay, and I'll do this one dotted, but I'll do it in a different color, and this triangle in green. Right, so I want to prove these two triangles similar. So I'm going to start off by just trying to figure out what angles do I know are congruent. Well, I know they both share angle I in there, so I could say that. And notice that, excuse me, angle H and angle J both share the same intercepted arc. They both share arc GK. Meaning, angle H and angle J have to be congruent. So I could start off by just saying that these two triangles are similar, much like we did the last one. I could say triangle IHK is similar to triangle IJG, oops, it's a terrible G, the AA theorem. Okay? If that's the case, I could set up a proportion of, or a proportion, yeah, of similar sides. So I could say IG over IK. Now let me just erase some stuff here so it's a little bit easier to see. I'm going to redraw those triangles. Okay, IG being the side opposite this one dasher, and IK being the side opposite the one dasher in this triangle, is going to be equal to IJ over IH, two more corresponding sides. So IJ, right, being the long side in that triangle, and IH being the long side in that triangle. So why are they, or why can we make that statement? Right, similar triangles have proportional sides. And if I can say that, if I use my same property of cross multiplying, I should be able to come out to that rule we started at the beginning. I could say IG times IH equals ik times ij. And again, cross multiplying would be the reason why. So again, notice that's exactly what we had above. ig times ih is equal to ik times ij. All right, lastly, to make your lives easier, I'm not going to make us do a proof for this. If you want to check out the proof, you can check out the proof on Canvas. The solutions are up there. But what I have here is a tangent line and a secant line. In my rule, just to get it out there quickly, is that nm squared, so side nm of that tangent times itself, is going to be equal to np, so is equal to the segment outside the circle, times, times, switch colors, times the entire segment, the entire secant segment, which is NO, which is that whole guy, right? So it's sort of a combination of our first two theorems. So the outside tangent line squared is equal to the outside part in red times the entire length in black, NO. Okay. Again, the proof for this, a little bit more drawn out. I don't want to make the video too long, so we're going to leave it at that. If you want to check it out, please check out the solutions on Canvas. All right, so those are the only three rules we're going to learn today. Let's maybe do a couple quick examples, and then I'll let you go. So the first one here, it says find ML and JK. Well, I have two intersecting chords, and if you remember, when you have two intersecting chords, the two kind of mini chords multiplied by each other should be equal. So I could say that x plus 2 times x plus 1 is equal to x times x plus 4. Now I know you all will remember that when you multiply these two guys together, you have to FOIL. So this would be x squared plus 2x plus 1x plus 2 should be equal to x squared plus 4x. If I combine my terms, I get x squared plus 3x plus 2 equals x squared plus 4x. This is nice. The x squareds cancel out. If I move this 3x over to this side, I'm left with x equals 2. Okay. If we look at these next ones, problems 1, 2, and 3 under problem 2. Okay, kind of gives you a mixture of a few of the different properties we learned about. Let's maybe do, let's do number 3. 1 and 2 are a little bit easier versions. Let's try number 3. This is the cases where I have two secant lines intersecting. So if you remember our rule, it's going to be the outside portion, which is 3, times the entire portion. So I have to add 3 plus x plus 2. That's going to be x plus 5. That's going to equal x plus 1, the outside portion, times the entire thing. I have to add x plus 1 and x minus 1 together. They add together to be 2x. All right, so now that we multiply, we get 3x plus 15 equals 2x squared plus 2x. Now I'm going to move all my terms to one side. 2x squared minus x minus 15 equals 0. If we factor, if you want to pause it for a minute and try to see if you can factor this, I'd encourage you to give it a shot. Excuse me. If you can't do it, or you just want to watch me do it, it does factor out to 2x plus 5 and x minus 3, which means my solutions are x equals negative 5 over 2 or 3. But you'll notice when you plug negative 5 over 2 back in, that gives you a negative value, negative length. We can't have that, so we have to throw it out. Okay? Number 3, I would encourage you to pause the video, see if you can figure out number 3. and then I will work through the solution in a minute. But try pausing it, see if you can work it through, and then we'll see if our answers match. You could use a calculator for this one, by the way. You could use a calculator, so if you want to get that out, you can. All right, so here's what I have. I have a secant line, or excuse me, a tangent line with a length of 203,000, and I have a secant line with a length of x, I don't know what it is, and an outside portion of 83,000. So if you remember our rule for secants and tangents, it's just going to be my tangent squared, 203,000 squared, equals the outside portion of my secant, so 83,000, times the length of the entire secant, right? Which I could call x plus 83,000, or I could just call it dB, because that really is the length of the entire chord, right? Or the entire secant. That entire length is BD. So I'm just going to call that BD. If you get your calculator and do it out, you'll find that BD, if we round to the nearest mile, should be equal to, or kilometers, excuse me, is 96,494 kilometers. So there you go. That's your introduction. Try to work through the solutions if you need them on Canvas. Homework is the circled problems from worksheet number 9. Hopefully you got them from my desk. And hopefully I'll see you on Zoom our next class.